Hi everyone, this is Worksheet 8.2, Derivation of Beer's Law. And this is going to be an interesting worksheet because this is one of the only cases, possibly the only case in this class where we're actually going to solve a differential equation. And we've seen a lot of differential equations, we've seen a lot of solutions to differential equations, but on this one we're actually going to solve it because it's one of the types of differential equations that are possible to solve in a relatively short period of time. So let's begin. Okay, first we should define all of our terms. This di lambda is the change in intensity of light passing through the sample. And then I lambda, actually to be more specific, we should say of wavelength lambda. Okay, then the next one, I lambda, is the intensity of transmitted light, also at wavelength lambda. And then this I0 lambda is the intensity of incident light. That is the light that hits the sample and hasn't passed through it yet. And then M is the concentration of the absorber, which most likely it's a solution of some kind. Maybe it's a solution of dye or some other absorptive material. Okay, and then epsilon lambda is the molar absorption coefficient at the wavelength lambda. And then dl is a tiny thickness of the sample. Okay, so now that we have all of our terms defined, let's take a look at the actual system. Okay, let's start with this one on the right. We've got the incoming light at a given wavelength. That's the incident light, remember? And then we've also got an intensity of transmitted light through the sample. And inside the sample, we've got our absorber that is absorbing photons, and clearly the intensity leaving the sample is lower than the intensity that is entering the sample. And we can say that the entire sample is of length L. Now imagine that the sample gets divided up into a large number of thin little wedges, really tiny wedges, like infinitesimally small. And you can imagine that the intensity of light near the beginning is going to be fairly high, but the more the light goes through the sample, the more it's going to be absorbed and the lower the intensity will get. So now take one of those little wedges, for this one over here on the left. And the little wedge is of length dl, and then we'll call the intensity of light coming out this side intensity lambda, and then we'll call the intensity over here on this side intensity lambda plus di lambda. Okay? So the difference between the intensity on either side is just that di, which is the amount that was absorbed by that thin little wedge. And what does di equal? Di lambda is going to be equal to negative molar absorption coefficient times the concentration of the absorber times the intensity at that location times the tiny little length of that wedge. Okay, so first of all, why is it negative? That's because the change in intensity is going to be negative. The intensity is going to go down. So that's why there's that negative there. And then you can imagine that it is also dependent on the value of the intensity itself, because if it's at a very high intensity, then there's going to be a large change in intensity. And if the intensity is already low, then there's going to be a corresponding low change in intensity. And this is an example of a differential equation. And we're going to see how to solve that one right now. And once we solve it, we will get Beer's law. Okay, first of all, I'm going to write out this equation in a slightly simpler form because it's a little bit cumbersome to have to deal with that function as lambda. So I'm just going to write it as epsilon m I dl, like that. Now the next step is to get I on the same side of the equation. So I'm going to divide both sides by I. And what do I get? I get 1 over I di equals negative epsilon m dl. Okay, so now I've got two something like derivatives on either side of the equation, and the way to get rid of those on either side is to integrate both sides. And we're actually going to integrate from 0 to L for both of these. And the integral of this side is going to be equal to log I minus log I 0, because this represents the intensity of light that is at position 0, and this represents the intensity of light that is coming out at L. L and 0. Okay, and then the integral on this side, I just can pull the E and the M out because I can assume they're constant all throughout the sample, and then I get the derivative 0 to L dl, and that just becomes L minus 0. Obviously, anything minus 0 just equals that thing. So this becomes negative E m L. And then when we're all done, we get log intensity minus log incident intensity equals negative E m L. Now I need to use the rules of logland to convert this subtraction into a division. So I get log intensity divided by incident intensity equals negative epsilon ml. Now I raise E to both sides of the equation, and I get I over I naught equals E to the negative epsilon ml. And that's Beer's law right there. And now I can put back in the fact that I'm talking about the function of intensity at a given wavelength. Negative epsilon wavelength ml, like so. And that's it. That's Beer's law, or the Beer-Lambert law.